Hey, John here. Let's try to wrap up the first release of the direct map cache code. I think I got this figured out. There's two main things that I'm going to try and release and talk about in this video, all right? The first one is, here, I'll show you what I messed up and why it wasn't working. It turned out to be very simple. It's a very common mistake to make. And the other one is a bit of an optimization that I overlooked that somebody pointed out in one of the YouTube comments. With that in mind, here's a video from last week, right? Part 5 of the direct map cache video. When I didn't quite have it debugged, which I got it now, and it was improved a little bit by, I'm guessing that's ASCII. R-I-C, is that an H? That's an A. That's got to be Richard. Thanks, Richard. Whoa. No, weird listening to yourself on the YouTube. There's an experience that's just weird. Anyway, moving on. Richard here, what is he doing here? Thank you, blah, blah, blah. And then he goes, you know, why are you doing this when this is better? The answer is because I wasn't thinking. For the most part. In my defense, if you go back and remember you watching those other videos, I changed which registers were used for what purpose halfway through and messed up a few things. And after I made that change, it turned out that his recommendation is far more useful. Let's not just look at the whole code. We don't really need to do that. Let's focus on what has changed since last time. Get tag minus N6 will tell us all the tag numbers as well as the comments. So this is the tag that went along with the video I released last time, which was, you know, the bias write was not working. So I then made some changes and kind of got ready to release it again. And then Richard over here chimed in. So let's see what's the difference here. Get diff minus R, and then you put this tag in there. So this will show me the differences between what's sitting in my directory right now and the tag that I released in the last video. And it is this. So this is what I'm going to release for this video. This is my first release of the direct map cache officially. So hopefully there is no more bugs left in it. I've done a couple of tests that make me think that it's probably okay. Please chime in if you find any issues. As far as I know, we're good. So this is the Retro ASM. This is the BIOS code. I turned off the debugging in there. I have what? I no longer am using the no cache version, and I'm now using the direct map cache version. So that's the only real changes to the BIOS. Last time I also turned off the console debugging stuff when you hit the escape key and things like that. So, yeah, that doesn't show up in the diff because I never actually committed that. You have to turn that on yourself if you really want to play with it. So what's happening over here? This is the direct map cache file, changes since the last video. Turn off the debugging, okay? And here's the comment from Richard. Don't do two when one will do. You have to be careful, though. This is an exchange. It swaps the contents of DE and HL. It does not copy HL into DE, which is what these instructions here would have otherwise done. The reason this is so reasonable to do is because right after I do this, I smother the HL register anyway. So we can go ahead and do a swap and discard what was in HL. And by the time this instruction here, which follows it, is done, the same effect will happen anyway, with half the bytes and half the time wasted. Okay, what else we got in here? I forgot to print a carriage return somewhere, which messed up the debugging output. Here's another one of these situations where this works better, provided again that you, make sure that you're okay with clobbering HL as a result of this process that's happening here. What else? Here's another. No. This is not me changing over to an exchange. This is, I was printing out the wrong register in this debug output here. Instead of printing out DE, I was printing out the contents of HL. So that was just a real bug, but not it's going to crash the program or anything kind of bug. It just printed out the wrong variable, so to speak, when I was trying to execute the debug statement. I removed my this doesn't work warning, and here's another exchange, followed by this. Now, this is a weird situation. This is what caused the problem. Okay? If you ever push too much in the stack and you don't then later on pop it back off, if you're a Z80, if you're used to stack machines, you know that's a problem. So it didn't match up. This was the number one problem that we ran into last week. This one little thing. So I wasn't paying enough attention when I was doing the refactoring of the code and getting these routines factored out. So, yeah, that's it. There it is. It's an embarrassment. Yeah, whatever. Moving on. What else happened here? I printed out the wrong register again in some debug code. And what else am I going on here? I added some comments. I removed my, well, that's interesting. There's a pop HL. This was actually part of the problem, by the way. This would have balanced the stack as long as this jump was not taken. But if the jump was taken, which was the normal case, by the way, the successful case, then what happened is the stack was messed up. So this was, the stack was half messed up. All right. And these comments here are, upon further review, this is utter insanity to even consider this. So it's time to delete the evidence. Okay. No, we will not invalidate the cache if we find out that we cannot write to the SD card. And the reason that makes sense is because the cache is not invalid. The SD card might be invalid, but the data in the cache is coherent and correct. Just because I can't just copy it onto the SD card, that's not a problem. So no, this thought goes away. Here's another problem that would have occurred during the failure case. This is just embarrassing, but it is a result of refactoring the code. As I mentioned last time, I changed, well, actually I didn't change anything. When I refactored the code, this is the, obviously the cache flush logic that's part of the writing operation. When I refactored this out of the write logic, the original write logic used the value in the accumulator to represent a status. And it's send it back to the BDOS that way, okay? And we still do that, but that's in the write code, not in this factored out code. The factored out code returns a failure if the zero flag is off. Loading a value into the accumulator does not change any of the flags. This is a rookie mistake, okay? But I'm going to go with it. This is a refactoring mistake. I factored the code into here and wasn't paying attention and then made a... oh, yeah, all right, a rookie mistake. You have to, in this case, clear the zero flag. And the easiest way to do that is just set a bit in the accumulator with an actual ALU operation that will result in the zero flag turning off. Okay, so this returns the failed status from this cache flush logic. What am I doing here? I improved some cosmetics of a debug statement. Here, what's going on here? I just added some documentation cleanup kind of a thing. Here's another one of the cases where an exchange is a better idea than the 1 byte at a time. Exchange is better than 1 byte at a time. Guard against those who don't read the doc. We don't have to do that anymore because the code, as far as I know, is working correctly. We saw that last time as well. What did I do here? I improved the wording in here a little bit. In a comment. What's going on here? So it goes on down here. I talked about this before. When the write routine fails, I had a single generic message in there originally, and it just simply said this: the pre-read failed, and we go back into the BDOS, all right? Along with another thought about whether or not to invalidate the cache, and the answer is no. Well, flushing the cache cannot invalidate it in this design of a direct map cache. So again, bad John, bad thinking. Okay, but this message makes perfect sense if indeed we fail during a cache pre-read. Okay, when we call the cache slot fill routine, that's fine. But if we fill the cache slot and then we update the sector in there and we go to then flush it back out, or if that cache slot happens to already have been filled earlier and we copy the sector we want into it and we go to flush it out and it fails while flushing, I want a different error message to be printed out. Okay, so what I did is I added some more jumps down here and some twisted stuff here during the during a failure. All right, this only affects if there's a failure. Do I want to get the right answer? Do I want to get the right message, I should say, printed on the console? So that was what this is all about. And you can see what do we got going on here? We fall down in here and print the I can't read the cache slot. Print it out, and then we go to BIOS write error, which is right here, where we set the accumulator to 1, and then we go to the normal return logic, which goes back to the BDOS with 1 in the accumulator, which is the error report back to BDOS, as we talked about before. This is the obviously original code down here, right? Now, if we fail during the write flush, obviously we then come up to here and then fall through and do the same thing. All right, so 2 different ways to return an error with 2 different text messages in there, okay? So that's what this is going on down there. And I changed what? Instead of hard coding the debug wedge, which is the handler for when I had an escape key from the console, and it used to call this debug wedge routine, right? Which is now commented out in the BIOS code. I changed that to instead of being hard coded on all the time, it'll be on if I turn on the read and write debug flag. So those are the main modifications. So if we compile it up, burn our SD card, put it in the retro board and reset. Boot it up with the debug off, and it's quiet. Presumably it's working, right? Well, we can do a simple save, right? We can save 128 pages into a file called ZZ. It should be, what, 32 kbytes? And when it's done, it should do a, I don't know if it does a warm boot or not. Well, we just created a file called ZZ anyway. And it didn't say there was an error, and it is 32K with 256 records, because remember the save command saves 128 256 byte pages. That's how that thing works, right? And it saves it starting from address 100. Now, the reason save works the way it does is it kind of goes along with how you might, if you want to do a hand manual, hand-done linking of some hex files after you've assembled some program, all right? If you want to hand link it, in other words, you can come into DDT and you can load files and manipulate them and move around the memory. And one of the things you can do is fill memory from address 100 to address, let's say, what, A000 with like a 41 in hex. It should be a capital A, right? So if I say dump 100, there's a bunch of A's, and it'll go on for a long time. Now, when I'm done with DDT, I can hit Control-C. It will do a warm boot. You see that happen very quickly because it did the warm boot out of the cache instead of the long way. Now, if I type save, 128, let's say YY instead of ZZ, it's going to save data out of the memory, starting at address 100, into the SD card, using all of our newly found write logic. And we should have a ZZ and a YY. Okay. Now, because we created the YY file from memory that has printable data in it, we can now type it. If we typed out the Z file, it's just got garbage in there, random binary stuff. Well, this is somewhat anticlimactic. You might think it crashed, but it didn't. Okay, there's the prompt. Because Minicom comes up by default, at least in this configuration, with line wrap being turned off, which can be a little annoying. Let's do this again. And obviously now you're going to see 32K bytes of A. All right. So does it work? Probably, right? We wrote in all A's. We got all A's back. I don't know what would have been written into ZZ, whatever garbage was in the memory after it had booted, right? There's something else we can do if we really want to. We can use pip to make a copy. We could say, whatever, yy2 equals yy. And in doing so, we know this file is all filled with printable ASCII characters. In other words, there's not a control Z or an EOF in there. Okay, because we formally padded it all out with A's. So we can do this. Now, if it was binary and you wanted to copy the whole file, you'd have to put an O in square brackets. I should probably do a couple of videos on how to use these commands if you're not familiar with them. So this is going to do a binary file copy, which is going to be the same thing in this specific case as a regular old, here I want to copy an ASCII file kind of a copy. And if we do a stat like so, you see them should both be in there. And if the copy worked, yy2. All right, and we got all A. None of this is really, rock solid definitive proof that things are working. However, it is pretty good circumstantial evidence, okay? Let's now try this. Let's do a pip. yy3 equals yy. Why me? Okay, so 1, 2, 3, 4. Let's just do 4 of these. So 4 times 250, what is it? 4 times 32K. Yeah, this is 128K total then. We're going to make a big file by copying another file 4 times, appending it to the end of itself. This might take a few seconds to complete. Because remember, we're only running at about 150K bits per second. The blazing speed of a single density floppy, which, by the way, a single density 5 1/4, single-sided, like on a TRS-80, the entire floppy could only hold about 80K bytes total. So this is already bigger than an entire 5 1/4 inch floppy. So in terms of time, those of us that remember formatting a floppy disk on an old TRS-80 with an expansion interface, a single-sided floppy, how long did that take, right? Only a good 30 plus seconds. So, yeah, this is pretty realistic. Oh, boy. Maybe I shouldn't have done 4 copies of it. All right. Finally, it finished. What do we got going on there? 128K. Boy, look at the size of that file. It'll probably go on the screen faster than it wrote the. Well, actually, it shouldn't. At 115.2, it should take about. It'll take longer to print the whole thing to the screen than it did to write it onto the SD card, most likely. Although, without the intelligent logic to skip the pre-reading of sectors, if you think about it, at 150K bits per second, and that is, the peak rate, of course. Let's assume it runs at the peak rate the whole time. If that's the case, and it has to pre-read each one of the sectors because we didn't really optimize our cache. We have the cache, but it's not as good as it theoretically could be, all right? It's probably really running at 75K bits per second. So if I type this out, it probably will go faster than it took to write the thing onto the SD card. And it'll give us a shot to see if we really did copy it all correctly. All of a sudden we see garbage coming up on the screen, we know that something weird is going on. Not bad. All right, this is, again, not the best way to test this whole thing, but I think it's working. I really do. If I hit escape, you can see that it's not falling into the debug handler, so all the debugging output has been cleaned up. So I think this is pretty good. I've actually done a bunch more tests I won't bore you with to make sure that I feel happy with this before I really do roll it out. But I think we're pretty good. I really do. So let me know what you think in the comments below, or post, mods, notes on GitHub. Pull requests, always welcome. Thanks for watching. I'll see you later.